we always study what are pure states, the states that can be represented as elements in Hilbert space. But when you have statistical mechanics, you will have also what are called mixed states. Mixed states cannot be represented as vectors in Hilbert space. So mixed states have to be represented by density matrix. So if we have pure states can also be represented as density matrix. For pure state density matrix is same as the projection operator. Whereas for mixed state, it's a probabilistic mixture of the density projection operators.
The entire matrix acts as a combination.
Entire matrix is the combination. Slater determinant is still a vector in a Hilbert space, in a multi-component Hilbert space. But here you cannot define a Hilbert space. Here the space in statistical mechanics, space is not Hilbert space, but it is an it's a set of bounded linear operators on the Hilbert space. That means now I have to consider set of all operators on the Hilbert space. Density matrix becomes a member of that space, operator space. So that is the space on which a general, either pure or mixed state is defined. Sometimes it is called Hilbert-Schmidt space. Hilbert-Schmidt space is set of all bounded linear operators on the Hilbert space. So density matrix belongs to that space. Okay, so that is what is the quantum state for a general pure or mixed state. See, just to give you an example, if I consider a box in which I have, let's say, spin of particles, and each particle is in a state called 1 by root 3 times up plus root 2 by 3 times down. This is the box A. Okay, I have another box, let's say box B. Here I have, so there are n particles. N particles, the state of each particle is given by this. But here I have n by 3 particles in up state and 2n by 3 particles in down state. Okay. Now, if you make a measurement of the state of the particle, you will get the probability to measure up state is 1 by 3. If you pick up randomly one particle, probability that you get up state is also 1 by 3. But these two things are different, because one is each particle has a definite quantum state, whereas in the other, even though each particle has a definite quantum state, it's a mixture, it's mixed in a classical sense, like blue balls and red balls in a box, up spins and down spins are mixed. They have a specific state, they are not in a superposition state. But yet, if you were to ask what is the state of one particle, you tell me what is the state of one particle, I do not know specifically, but here I have the answer specifically. The state of any given particle is this, and which is same for all the particles. But here, I have no knowledge of what is the state of the particle that I am going to pick up. So it's a mixture, statistical mixture. So I only know the probabilities, but I do not know the coefficients of expansion. Here, I know coefficients, I can get the probabilities. But if I know probabilities, I cannot get the coefficients. Because there is, if I know mod square, I cannot get mod A, because there is a possibility of infinitely many A's that you say mod because of that phase. So it is always possible that you can have a relative phase, and it turns out that it is a non-unique description of the quantum state. So here, this is called a mixture. So we have to describe the state of such a system by a mixed state. So I have to write this as a density matrix with 1 by 3 times the projection operator corresponding to up, plus 2 by 3 times projection operator corresponds to down. This is the only description that is suitable to describe the mixed state. So I cannot write, so no alpha in the Hilbert space in this case, the Hilbert space is C2, two-dimensional complex vector space can be used to describe the mixed system. So you have to necessarily go to an operator space. Talk about set of boundary linear operators. And then
For n equal to 1, this is the
for n equal to 1. See, if it is n is equal to 1, you have this particular. So what state it is, you will put in one of these states, right? Here there is no particle in this state. Even though probabilistically both are same.